Lecture 15 is about the stereonet. This is a graphical tool used by structural geologists to represent orientation data in 2 dimensions. We can understand the stereonet more easily if we first think about a sphere. Imagine an observer standing at the center of a large hollow glass sphere. Any direction can be specified by marking a dot on the surface of the sphere. For example, east can be indicated by a dot on the equator of the sphere that is east of the observer. And up will be a dot on the surface of the sphere that is directly above the observer. The early Greek astronomers used a similar method. They displayed the relative position of stars by plotting them as dots on the surface of a sphere whose center was the Earth. This was called the celestial sphere. Now, let's consider lines and planes. Any line passing through the center of the sphere will be represented by a dot on the surface of the sphere. And any plane passing through the center of the sphere will be represented by a circle on the surface of the sphere. This circle is called a great circle. You can visualize this using a cereal bowl. Any line passing through the center of the bowl will be represented by a dot at the surface of the bowl. And any plane passing through the center of the bowl will be represented by a semicircle on the surface of the bowl. Note that by using a bowl, we are considering the bottom half of the sphere or lower hemisphere. This is a standard practice in structural geology. However, carrying around a sphere or a bowl is rather cumbersome. We need to reduce this spherical projection to a piece of paper. For a line, we can do this by projecting the point of intersection of the line with the bottom half of the sphere to the topmost point or zenith of the sphere. The ray to the zenith intersects a horizontal plane of projection passing through the center of the sphere, at a point. This is the 2-dimensional representation of the line. Likewise, for a plane, we can project the points on the semicircle representing the plane, to the zenith of the sphere. The intersection of these rays with the plane of projection will define an arc. This arc, or great circle, is the 2-dimensional representation of the plane. This kind of projection is called a stereographic projection. The circle on the projection plane is called the primitive circle, and it is like the rim of the bowl. We need to consider an additional element, and this is a small circle. Planes that do not pass through the center of the sphere intersect the sphere in small circles. These small circles project as circular arcs on the stereographic projection plane. Now we have all the elements to construct the stereonet. First, we will consider north-south striking planes, dipping to the east and to the west, from the horizontal to the vertical, at a regular interval of, let's say, 10 degrees. These planes are illustrated here as equal-size protractors of different inclination, from the horizontal to the vertical. And in the projection plane, they are represented by great circles, as shown here. Next, we will consider cones with horizontal axes, apex at the north or south, and apical angle 0 to 90, at a regular interval of, let's say, 10 degrees. These are small circles, and in the projection plane they look like this. By putting together the great circles and the small circles, we can construct the stereonet. In this case, the interval between the thick lines is 10 degrees, and the interval between the fine lines is 2 degrees. The north, east, south, and west directions are marked on the primitive circle. This kind of stereonet is called an equal angle, or Wolf stereonet. It is called like this, because this stereonet preserves angular relationships. For example, small circles of 10 degrees apical angle will plot anywhere on the stereonet as circles. However, these circles will be smaller towards the center of the stereonet, and larger towards the primitive. This is not very good for looking at the distribution of data, for example lines on the stereonet, because equally distributed data will look more concentrated towards the center of the stereonet than near the primitive. Therefore, in this class, we will use another type of projection called the equal area projection. This figure shows a vertical plane through the sphere. A line passing through the center of the sphere intersects the sphere at a point, here shown in red. In the equal area projection, instead of projecting this point to the zenith, we project it to the base of the sphere, along a circular arc with center at the base of the sphere. We then scale the distance of this point to the base of the sphere so that it fits the radius of the sphere. In this case, the scaled distance is x. Finally, we project the point back to the horizontal. The blue dot is the projection of the line in the equal area stereonet. This is the stereonet resulting from this kind of projection. It is called the equal area or Schmidt stereonet, and it is the stereonet we will use in the course. The equal area stereonet preserves areas. 10 degrees small circles don't plot as circles everywhere, but they all have the same area across the stereonet. This is great to visually inspect the density of data on a stereonet. To better understand these concepts, read Chapter 5 of either Marshak and Mitra, or Reagan. And answer these questions.